Good day, everyone. So, welcome back to the second session of covering the photoelectric effect, chapter 16, which is the third chapter in unit 3, which deals with optics and light. So, before we move on to this session, let's go over what we have seen previously in the first session. So, in the first session, we covered mostly experimental data and we defined some terms that we're gonna need for this session. So we went over photoelectric effect and what does photoelectric effect mean? Here is the definition. It's important to know these definitions because you might be asked about them in official exams. This phenomenon, the photoelectric effect, can be explained using the corpuscular aspect of light. A photon is a particle of light or quantum of light having zero mass and zero charge. It's important to know these things. A photon carries a unit of energy given by the equations h nu or hc over lambda, 1 electron volt, we talked about it. And the condition to observe photoelectric effect experimentally is the energy of the photon should be greater than the threshold or the work function of the metal. The frequency of the given photon should be greater than a value we defined as threshold frequency, and the wavelength should be less than the threshold wavelength. Again, these three terms need to be known by definition. So you can go over the previous part or to the course that you can find in your books and memorize these definitions. You should be able to answer the question of how to define these. Now, work function here is the minimum energy required to extract an electron from the surface of a metal, and I added here a note with no kinetic energy. You might ask, what does that stand for? I added this within parentheses so that in the upcoming part, we'll talk about it in more details. Right now, let's move on to our session. So, what are we gonna cover in this session? First, we're gonna go over the photoelectric effect as interpreted by Albert Einstein, which is required in our curriculum. We'll go over the quantitative study of photoelectric effect, and we'll do some calculations regarding the photons, the light that we use, and everything else. And we're gonna have a look about the electric current produced by the photoelectric effect. So starting with the first term, which is the photoelectric effect, Einstein's equation. Now, before we start with Einstein's equation, historically speaking, in 1905, Albert Einstein, forget about Max Planck now, Albert Einstein explained the photoelectric effect. I need to give it like 30 seconds to talk about this just out of respect for the history. Albert Einstein is recorded to have explained the photoelectric effect in 1905. Nevertheless, another German scientist who is Max Planck also explained the photoelectric effect. And before these two, in the late 1880s and in the early 1900s as well, other scientists tried to explain the photoelectric effect. But historically speaking, the calculations that we're gonna do are referred to as Einstein's equation because Albert Einstein got Nobel Prize for this effect in 1905. So this is just a brief idea of history. You can read about it wherever you want. You can find on Google a lot of sites that explain this. Anyway, in order to do this, they added some basic ideas, Einstein and Planck. What are these ideas? First, they said that light is a stream of photons, each carrying an energy, E gamma of, and you know that there should be no D here, okay? Second idea they added is, one photon interacts with an atom at a time. It's important to know this. One photon at a time. We cannot have more than one photon interacting with the atom. Now, what does that mean and how does that help us explain? Okay, suppose that a radiation, some light falls on a certain metal surface. Electrons are found here, okay? Now we need to extract these electrons to produce the photoelectric effect. According to Einstein, Planck, I will use Einstein from now on and the history can be studied whenever you want. According to Einstein, first he thought about the experiment as follows. if light, huge emphasis on if light were a wave and this wave reaches the electron, once the electromagnetic wave, between brackets light, reaches the electron, this one here, the electron, it will start vibrating more than what it is doing in the first place. Okay, thus this electron will start vibrating affected by this wave. Now, another wave reaches it. Notice here I used color coding to show you that the wave is progressing. Color coding doesn't have to do anything with the colors. It is the same light used here. Then more energy is given. Another wave comes. Notice here the red one moved away and we have the green part. Another wave reaches the the electron and gives it more energy. Thus it wiggles more, it vibrates more. بتهز أكتر وأكتر. كملنا أكتر. Another part of the wave reaches the electron and it starts moving more and piles up. It builds up more amplitude, it vibrates more. Over here, the electron had received enough energy, a lot of energy, and the electron exits and is emitted out of the metal. So this was an explanation using waves. Now, if this were true, we would have seen photoelectric effect sooner or later. بس هون بدي وقف شوي عندكم ونجرب نتذكر بالحصة الأولى. بس عملنا الاكسبيرمنت بضوء معين ونطرنا شوي ما طلع electrons. So this theory is completely wrong. This theory is completely wrong. We could never explain photoelectric effect using the wave nature of light. And that's why Albert Einstein and Max Planck had to suggest this. One photon at a time, not a continuous wave or something like that. Now, once this photon reaches the surface of the metal, two cases can be distinguished. The first case is if the energy of the photon is less than the work function, no photo emission will happen. So it reaches here, nothing happens concerning electron emission. Will there anything else happen? It's not our subject now. The second case is if the energy of the photon is greater than or equal than W0 or Ws, here it's accidentally forgotten, okay? You can call it W0, you can call it Ws. Concerning names and vocabulary that we used, these are like general ideas. Some people might use it W0, some people might use it Ws, some people might even use it as letter phi, okay? So again, I just give you these notes so that no one thinks that this is correct, this is wrong. All of these are correct and accepted. Now, if the energy of the photon is greater than or equal than the work function, an electron is extracted. Not only that, the electron is extracted and the energy that the photon gives is taken by the whole system here. Part of the energy will take the electron out of the metal, okay? كأنها عم تدفع عليها ديناتها لتظهر من الميتال, and the remaining energy, if any, will be acquired by this electron as kinetic energy, which we know half mv squared. So the interpretation of Einstein was the following: an electron is emitted out of the atom, expelled from the metal إذا بدكم تسموها, and given kinetic energy such that kinetic energy equals energy of the photon minus W0, or Ke equals h nu minus W0, or even hc over lambda minus nu. Now, when you read this equation, first it's known as Albert Einstein's equation or Einstein photoelectric effect equation, okay, even though it might be given by other scientists as well. Now, when you read this equation, or if you go to Google and search for it, you'll notice that Ke is written here as Ke max. It's given like it is a maximum value, okay? What does that stand for? We'll talk about it. Before I move on, here I've assigned on page 280 in the official book, exercises number 10 and 11. After knowing the Einstein equation, you can go over these and solve them and check with your teachers about their answers. Maybe we can post the answers later also with the link of this episode. Now, so back to the photoelectric effect equation given by Albert Einstein. So the electron is emitted out with given kinetic energy max equals. I replaced the photon notation by gamma. Okay, I'll try to use it photon usually, but if I ever use it gamma, just to agree on it. Now, Ke max. Why maximum kinetic energy? Usually when the electron exits or is expelled from the metal, not all electrons move at the same speed. Not all electrons move out of the metal with the same energy, because you know that a metal contains a lot of atoms. So a lot of interaction will take place. That's one. Number two, to measure this kinetic energy, we use something away from our discussion, which is not required in our curriculum. And that method is able to measure the maximum value of kinetic energy. That's why when we write the rule here, we just rely on kinetic energy maximum of the fastest electrons present. No need to worry about it once again. We just need to know that the equation talks about kinetic energy max. Now, in this part, I added graphing because we're going to focus a little bit on the graph given by this. Okay? So first we'll go back to the PhET simulation, the simulation that we have seen before. Now we can talk about this experiment more. Okay? This is known as the cathode tube, and you have here a battery which is used to measure the kinetic energy max that we talked about. Now this is not our subject. Our subject is only to study the emission of the electron. طيب هون بدي ركز على فكرة تانية بس. الالكترونز اللي عم بيطلعوا عندهم kinetic energy, which is half mv squared, and which we can measure. Now in this part we focus on the graph. So if I start up with this, I'll increase the intensity. You notice that electrons move out with some energy. Now there is something nice about the PhET here, that it can produce electron energy versus the light frequency here. It can show us a graph that when we change the frequency, or here the wavelength, how would the kinetic energy change? I will choose here different values, okay? And you can notice the line produced here, okay? So that's the first graph. We have an inclined line passing by a certain point. We can talk about it later. If I change the metal to zinc, let's say, and I also do the same thing, you notice the same thing happens, okay? Over here, look, as if the point is moving on the horizontal. We got a similar line, trace the same graph. If you look at the graphs, somehow they seem to be parallel. Why is that? And why is it a straight line? Let's talk about this in this part. So we close this. Okay. So when we set Ke equals HU minus W0, and we compare this to something we know in mathematics. In mathematics, this is similar to an equation given on y-axis Ke, and on x-axis we place in u, the frequency. So this equation becomes similar to y equals ax plus b, right? So this equation, let's erase this part so that, since it is written, okay? So by comparison of this equation, okay, of this equation to the general equation of a straight line, y equals mx plus b or ax plus b, as you are used to it, we know that the graph of kinetic energy versus frequency should be a straight line. And if you look at the graph here, you notice I've traced 3 graphs of 3 different metals regardless of their names. I have straight lines. Now these straight lines are parallel. Why is that? Think about it. Can you interpret why are the obtained lines are parallel here and in the experiment that we have seen in the simulation? Do you have any answer for that? Okay, as some of you might have noticed, since Ke, which is y, equals h nu, which is mx, thus the slope m is h. No matter what the metal is, we have the same slope. And when slope is equal, so same slope implies parallel lines. So that explains why the lines are parallel. And in order to calculate the slope, if you know h, you can use it. If you want to measure h by this experiment, you calculate the slope by using rise over run or y2 minus y1 over x2 minus x1. Now, on the other hand, the secondary part, the plus b thing, which we call the y-intercept, or some people call it ordinate at the origin, which equals by comparison minus w. So the y-intercept is b equals minus w0, minus the work function. So if I extend or extrapolate this line, إذا طولنا الخط مثل ما هو ودotted، هلا بنحكي ليش dotted. It cuts the axis here at a point minus W0. I added W01, 2 and W03 لأنه عندي 3 metals. Now, why dotted lines? هات لنشوف. Think about it. Try to think about a reason for why are these lines dotted here. So, one of the interpretations might be this, on the y-axis we have kinetic energy, which is half mv squared, which cannot be negative in our regular science. So kinetic energy cannot be negative. So when I draw a line here corresponding to a physical idea, I cannot have negative kinetic energy, so we extend it as dotted line, and no, it's a virtual extrapolation of the line. Now, what's special about this one here? Cutting the x-axis, or what we call the x-intercept. So if you think about it using mathematics, in math we know that x-intercept stands for, so I write it here, x-intercept is y equal to 0 in mathematics. Yani here, kinetic energy is 0. It's very important here. So if I go to the kinetic energy 0, I get h nu equals w0. So here we get ke 0. Or in other words, h nu equals w0. This nu here is the threshold frequency as we have seen before. So the x-intercept of the kinetic energy versing in the frequency line gives us directly the threshold frequency. And I've added them here with nu s1 and nu s2. Okay, so referring to each of the 3 different metals. Okay, so this is a graphical study about Einstein's equation. It is important for some exercises, and in physics we mostly rely on graphical study. So, شو المهم نعرفه من هون؟ Einstein's equation بتقلنا k equals h nu minus w0. إذا بعمل comparison مع equation of line y equal mx plus b بيطلع عندي فكرتين. أول وحدة slope هو h، والسلوب بنعرف كيف نطلعه. الواي انترسبت اللي هي b is minus w0 اللي هي الورك فانكشن، سو فيني طلعها اذا طولت الخط. وفكره ثالثه نحن جربنا فيها is the x intercept، محل ما بيقطع الاكس اكسس او هون الفريكونسي اكسس يعني. اوكي، سو باي سمبل كالكوليشن بدون ما نشرحها هلا هون فينا نعرف انه هي النقطه هي الثريشولد فريكونسي اللي حكينا عنها قبل. اوكي، سو هون خلصنا نحن الفوتو الكتريك ايفكت بشكل عام وحكينا عن الجراف تبعه. كنت قلت قبل انه فينا نروح على page 280 ونشتغل exercises 10 and 11 and you can check the answers with your teachers. Now I will move on to another part, to the second part of today's session, which is studying photoelectric effect quantitatively using numbers. So quantitative analysis، بنحكي شوي عن الأرقام. In order to do that, okay, a source of monochromatic light with a luminous power P emits photons each of energy E photon equals H nu. So عندي ضوء عم بيبعت monochromatic light، هون عم نركز على ضوء بفريكونسي وبلون واحد لحتى لي ما يكون عندي عجقة ألوان وعجقة calculation. كلنا بنتذكر power is energy over time. So the luminous power given by this source is given by P, is given as P. اعتبر عطينا إياها. And the photons given by this source افترضوا هاو كأنه photons عم بيمشوا هيك. اوكي؟ أو إذا تصورون مثل ما بدنا نرسم الفوتون فينا. اوكي؟ شوي شوي بنصير نتعود أكثر ونشوف أكثر كيف بينرسم الفوتون. اوكي؟ So photons are given in all directions. Now, what's the energy of each photon? Sorry for that. Okay, the energy of each photon the luminous energy, the energy of this source, excuse me for that, can be calculated by two ways. First, I can use the luminous power which is given E equal P over delta T, because we know that power equals energy over time. So energy is power times time. Okay, so this is simple. And on the other hand, and this is new, we can say it's N emitted multiplied by energy of one photon. عندي N photons عم بيظهروا من هالضوء وكل واحد عنده energy E photon وهي ذاتها لأنه monochromatic. So the energy of the whole source, or the whole energy of the source is N times E. هيدا واحد. اثنين. Before we move on بنتفق أنا وياكم على شيء اللي هو assumption بيزبط وين ما كان إلا unless otherwise indicated إلا إذا قال لي عكس هيك. The medium is assumed to be homogeneous and non-absorbing. بنعتبر إذا حطيت ضوء هون عم بكب photons أو light in all directions بنعتبر إنه بكل اتجاهات الضوء بيروح بنفس السرعة وبنفس الكمية. ما معقول يروح الضوء لهون أكثر ما بيروح لورا. أوكي؟ شو السبب؟ لأنه كل الميديوم اللي بنشتغل فيهم بنعتبرهم homogeneous كلهم معمولين من نفس النوعية and non-absorbing وبنعتبر الأهم إنه الضوء عم بيبعت energy هاي الانرجي هون وهون وهون على كل المنطقة بتضل ذاتها. So if the source gives 10 joules مثلا أوكي ما راح تصير بعد فترة 9 جول بنعتبرها على طول 10 joules unless إلا إذا قال لك إنه كل متر عم تنقص الانرجي هالقد. هيدا الشيء صار يمكن شوي advanced. أوكي So إذا ما كان محدد we assume these two ما في زوم نتفلسف فيها كتير ونقول يبلكي ما كانت هيك أو لا. We take it directly if it's not indicated. Now, حتى in a source, the source starts spreading its light everywhere. Sorry. So here's the source giving light everywhere. هون رسمت سفير تخيل هيك سيركل كبيرة عم بيوصل عليها الضوء وعم بيوصل بنفس الطريقة because it's homogeneous in all directions as we have said. Light is sent in all directions with the same ratio إذا بنسميها. Okay. So light is emitted from the source in all directions evenly بشكل متساوي. Luminous power is conserved. الباور اللي طلعها السورس بتضلها ذاتها وين ما كان. هلا لكمل كنت عم بستعمل كلمة وعلقت عندها شوي because I didn't want to introduce a term that we haven't talked about. We'll define something called luminous intensity. إذا متذكرين من السنة الماضية حكينا عن intensity مع الصوت with sound. Intensity is power divided by area. Luminous intensity is defined as the luminous power, الباور اللي مبعوث لهون divided by the whole area. وعلى ايدي نفس الشيء إذا وصل ضوء هالقد قد ايه الباور اللي عم توصل على ايدي divided by the surface area لكف ايدي we call that luminous intensity. So luminous intensity is the power per unit area and it is calculated as first before I move on to the second idea لأنه هيدي مثل overall idea. So intensity is power over surface. And how to calculate surface? Since light moves in all directions, so بتخيل أنا surface شكله sphere. And the surface of a sphere is given by the equation 4 pi r squared. R هي radius. Okay? تبع السفير اللي عم نحكي عنه. So if we consider it here, the power of the source, which is conserved وين ما كان, is distributed all over the sphere whose area is how much? 4 pi d square. d هي هيدي المسافة. The distance between the source and the surface where I am standing up or considering. Okay? Now, Suppose I was giving you an example of my palm, but it can be the same thing for a cathode بالاكسبيرمنت اللي كنا عم نشوفه من شوي مثلا. هيدا البليت اللي موجود بيسوى يكون محطوط بعيد عن source. So the plate that we are studying for photoelectric emission, the metallic plate, has a surface like وينه plate of surface S of P plate RSS. So the power received by the plate here من الفوتونز اللي عم بيوصلوا, the power received by the plate over the surface plate is also the luminous intensity. And since the medium is homogeneous, بما انه الميديوم homogeneous, بنعتبر انه كل هيدا السيرفيس مثل ما قلنا قبل عم بياخد even intensity متعادلة او متساوية وين ما كان. So when we divide power by the whole surface تطلع هي ذاتها هيدي الباور divided by هيدا السيرفيس. So this rule can be directly used. Definitely knowing how it was developed is important, بس كمان إذا بتلاقي مشكلة فيها you can directly use it as it is. Okay? By this we were able to link the power of the source to the power received by this plate, وبالبارت اللي قبل ربطنا الباور للسورس بعدد الفوتونز وبالانرجي اللي عم تطلع منهم. هيدا كله خاصه بالارقام وبيعتمد على السؤال هو شو عم بيطلب منك. اوكي؟ Over here I have an application كان المفروض نقعد نشتغله سوا، بس صراحة نظرا لضيق الوقت قلت بفضل احكي شوي عن كل فكرة بفكرتها، وهو الاكسرسايزز فيكم ترجعوا انتم يا تشتغلون لحالكم. مثلا هيدا رقم number 15 page 280 sorry number 15 page 280 بكتاب الاوفيشال بوك بكتاب الدولي. اوكي؟ If you don't have it, here is the exercise. Go over the playback of this session or this period وفيكم تشوفوا. الحل كمان يا بنحطه بعدين or you can refer to your teachers about it. Okay? Moving on. The current due to a photoelectric effect. كل شغلنا نحن انه electrons عم بيطلعوا. طيب how can I benefit of this? Basically when an electron is ejected from a plate, وصلوا هون ظهر الالكترون. Once the electron is ejected out of the plate, some current will flow here. نقصوا electrons, زادوا هون, etc. Okay, so we'll have a current flowing in the circuit. Yes? So when a photon is absorbed by the electron, when it is absorbed, an electron is emitted. Suppose that this electron is received by the other plate. It's important نعرف إنه الإلكترون اللي عم بيظهر من هيدا البليت مش ضروري يوصل على تاني بليت، بس نحن بنعتبر إنه عم بيوصل وبنشتغل على هالأساس، إلا إذا حدد لك شيء تاني. بس بالمبدأ نعتبر إنه فوق الإلكترون عم بيظهر من البليت عم بيوصل على التاني ليعمل electric current. Now, this photon which expelled an electron is referred to بنسميه effective photon. اوكي؟ electric current وهون رح امشي فيه شوي بسرعه لانه هو مراجعات من grade 10 is charge over time. will charge is the number of electrons equals number of effective photons. So التشارج هي number of electrons ضرب الإيت electric charge unit. هون أنا ما حطيت number of electrons دغري حطيت number of effective photons لأنه كل photon كان effective راح يظهر لي electron. Okay? So using this we can calculate the current. From the current we can find the number of effective photons. So لهون بنكون خلصنا الدرس تبعنا. مشينا شوي بسرعة. You can go over this session وتعيدون شوي شوي. أي فكرة بدها توضيح وقفوا عندها وشوفوها مرة تانية. هلأ راح أعوز بعد من وقتكم 3 ل 4 دقايق لنحكي شوي. أول شيء قبل ما أكمل هي سيشن 2016 GS أوكي مع شوية modification أوكي. So شوفوها هيك مثل ما هي هون. Try to solve it. Refer to your teachers مثل ما تعودنا على طول. اوكي فيها الابلكيشنز مباشره اللي حكيناهم هلا. ناو شو اهميه الدرس اللي شفناه لحتى يكون عم ندرس شيء له معنى. في شغلتين بدي ركز عليهم لانه اذا بدي احكي عن فوتو الكتريك ايفكت واهميته بحياتنا كل يوم صدقوا انه في كتير ابلكيشنز. انا نقيت شغلتين شوي من بيعنونا. First our calculators مثلا هون اللي بدي ركز عليه هي the solar cells that we use الشيء اللي تبع الطاقة الشمسية بنسميها اوكي بطارية الطاقة الشمسية كيف تعطي كهرباء it functions by photoelectric effect. sunlight هو white light فيه كل الالوان اكيد رح يعمل photo emission اوكي بصير في electrons بصير في electric current مثل ما شفنا بالبارت الاخير هلا هيدا الكارنت او بشغل فيه الكالكوليتر او بشرجه وبستعمله بعدين. The same technique is used هون بس نبعت artificial satellites على الفضاء ما بنعبيهم بطاريات نعطيهم solar cell بتستعمل photoelectric effect لتعطي كهرباء كمان الكهرباء يا بنخزنها or we can use it directly. Another important use is the quantum physics. شو يعني quantum physics؟ كثير بنسمع عنها إذا عم نحضر شي science fiction movie أو أي شيء. quantum physics هو branch physics متطور جديد متطور كثير وبلش in fact 1920 وطلوع اوكي بيحكي عن شو هو what is the nature of objects. When we studied photoelectric effect we said that light is a particle. طيب ما بالchapters اللي قبلها يا جماعة قلنا light is a wave. So light can be a wave sometimes, it can be a particle sometimes أو somehow a particle. طيب what is the nature of light؟ هيدي ولا هيدي؟ So this raised a huge question إنه يا جماعة تعالوا نجرب نشوف what is the nature of light. وبعدين وسعناها على كل شيء وهون صرنا عم ندرس quantum physics. Quantum physics is a branch of physics that studies small tiny objects, atoms, particles inside the atoms. So quantum physics was built on experiments such as the photoelectric effect. Now ending this session شو شفنا بهذا الدرس؟ هيدي الورقة هون فيكم تشوفوها كسامري لكل شيء أخذناه. تعريف photoelectric effect. This phenomenon relies on the idea of light being a particle and not a wave. A photon has the characteristics zero mass, zero charge. Now, electron volt والH already حكينا عنهم. To observe photoelectric effect ثلاثة conditions واحد منهم بده يكون فينا نحكي عنهم ثلاثتهم. الانرجي of the photon بتكون أكثر من الwork function. الفريكونسي بتكون أكثر من الثريشولد فريكونسي واللامدا أصغر من لامدا threshold. Definitions of threshold frequency هون زدت كلمة cut off ممكن إذا فتوا على جوجل تفتشوا فيها تلاقوا كلمة cut off frequency which is the same. Okay? Threshold wavelength and work function لازم نكون بنعرفهم and keep in mind فيكم دغري تستعملوها W0 the work function equals H nu 0 و HC over lambda 0. Now Einstein equation for photoelectric effect KE max equal E gamma minus or H nu minus W0 و interpreting the graph مع هودي نربطهم ببعض كتير مهمة. كمان إذا نسيتوا شيء عنها إنه هي شو معناتها السلوب شو قصته أوكي go back to the previous part that we explained. بس هيدا الاسنشال لازم نعرفه أوكي linking this to mathematics صارت شوية mathematical physics. To determine the number of photons in a luminous beam نستعمل هاي الإيكويشن and luminous intensity is the power per unit area and it's the same. هيدي اوكي بنستعملها إذا بدي أشوف how many photons are received by this plate بوقت معين. اوكي last part اللي هو الالكتريك كارنت هو additional part كان من عنا فيكم تزيدوا انتو ك part 11 او لا. nevertheless هيدي الشيت summarize everything that we have seen. برجع بذكركم انه بس نخلص هاي الحلقة it will be posted على الويب سايت. you can check the link and watch it whenever you want. وشي تاني انه رح نزيد البي دي اف اللي هو كل شي حكيناه موجود على اوراق. you can read them whenever you want. Stay safe and thank you for your time.